Okay, shall we start? Good morning, everybody. So we will here we have Professor Branton Campbell of the Department of Physics and Astronomy of Brigham Young University, and he's very famous in the developing one of the developer of ISOTROPY software suite, and also I remember that he is one of the leading person in the as a chair of the Commission of Magnetic Structure, and then this established MShift. It was introduced yesterday, and his contribution very large in this field, and probably because of this MShift, we can enjoy even beginners can start analyzing magnetic structure easily. So these two is very famous, and probably he will talk about relation to superspace group and magnetic superspace groups, and they also in commensurate structure. So this is one of the difficult things, but probably he clearly explained about that. Thank you. So let's start.
This one here. Okay, thank you. It's really my pleasure to be here. I'm excited to participate in the workshop. It's I think the first international workshop on magnetic crystallography in China and also in Asia, to the best of my knowledge. So it's really quite a significant event that we've all gathered together here for this purpose. So I'm going to start with an introduction to magnetic, incommensurate magnetic structures, magnetic superspace groups. I'm certainly not the world expert on this subject. I know something about the subject, but I think others like Manuel Perez Mato and also Margarita Henriquez, Françoise Damé, and more. Dmitry Kalyev, probably know more than I do, but I'm still glad to be here to participate. I'd like to acknowledge my primary collaborator, Harold Stokes. Harold is the originator of the ISOTROPY software suite. I've been collaborating with him on this topic for about maybe 19 years now, but he was the originator. I also acknowledge Zander van Smalen, Manuel Perez Mato, Václav Petracek, who's not here, and also Andrei Gubkin from Yekaterinburg. He helped me to identify some rather significant bugs in our original magnetic superspace group tables, and with his help, I've fixed them. So there are also a number of resources. I appreciated Manu's comment during his talk the other day. He said that it's not possible to learn everything from a presentation, but there are some resources here that you can go to. I recommend this book and also this nice paper by Manu if you want to learn more. So, incommensurate magnetic structures are becoming more and more common. We see them in very interesting materials, very interesting systems. These include skyrmions. This background picture here is a skyrmion lattice. And there's also a variety of topological magnetic textures and excitations. I think Dmitry Kalyev will be saying more about this soon. Multiferroics and a lot of interesting physics. If you look in the Bilbao Crystallographic server and explore the Magen database, you'll find that there are already currently 160 incommensurate magnetic structures. As of yesterday, I don't know, maybe someone submitted a new one last night, but the last time I checked it was 160. It's always changing. Each one of these structures possesses a symmetry group that we refer to as a magnetic superspace group. Now, when you distort a material, the distortion can always be decomposed into waves. You can always do this. It might be a simple wave, a single sinusoidal, or it might be a a superposition of many waves. Each of the waves has a wave vector, a propagation vector. I was really grateful that Javier Campo took so much time to explain propagation vectors. I think that was a very good place to start the workshop. So as a function of position, the value of the wave is modulated. It varies sinusoidally. If the k vector is 1/2, this is going to double the size of the unit cell. If the k vector is 1/3, it's going to triple the size of the unit cell. You can also, have your k vector with multiple vector components, like 1/2 0. The distorted structure, the lattice of the distorted structure, has lattice points, which, when dot producted into the k vector, have to give you integers. So, for example, if you dot the vector 1 1 0 with 1/2 0, you get an integer, and so this is a new lattice point up here. And of course, if you do 1 1 0 along this direction, you also have to increase the unit cell in the other direction. And so the propagation vectors dictate the size of the unit cell. Some modulated structures are multi-K. You can simultaneously have modulations along one direction and also along another direction. When you do this, the unit cell grows in both directions. And finally, you can have incommensurate propagation vectors. With the incommensurate propagation vectors, you have an irrational component in the k vector, and this means that the period of the wave is incommensurate. It's not simply related by some rational fraction to the periodicity of the underlying parent lattice. When you have an incommensurate wave vector, you never truly return to the same place, because after you complete one period, you're not quite at the original position in the parent lattice. And so, as a result, you get, in a diffraction pattern, you get these superlattice peaks that are called incommensurate satellites. So, for example, this is a structure I extracted from the literature, lanthanum strontium copper oxide. If you look at the period of these, if you look at the spacing of the satellites, and you repeat multiple times, so you go 1, 2, 3, 4. You don't reach the other Bragg peak. So, if you multiply the superlattice wave vector by an integer, you don't arrive at any new Bragg position. Thank you, Manu. Appreciate it. That was a very nice favor. I appreciate it. So the superlattice peaks are indexed not only by HKL, but also by additional integers. So, for example, if you want to arrive at this peak right here, you would go along the 110 go along the 110 direction. So this would be 11010. Or let's see, is that right? Yeah, I think that's right. So 11001 in order to arrive at that point. So you can appreciate that incommensurate modulations destroy the translational periodicity of your crystal. So you look here. It's nicely periodic, and you apply the modulated distortion, and you can see that when you arrive at a new lattice point, the atom is missing. It's moved over to a new position. At this spot, it's moved in this direction, and it's simply not periodic. The spacing from here to here is different from the spacing to here. There's no commensurate unit cell, no commensurate lattice when something like this happens. This curve that I've drawn is a transverse curve, but it's actually a longitudinal wave. This curve is just illustrating the amplitude of the distortion. And so we lose our lattice translations. In the traditional sense, it's no longer a crystal because you don't have a lattice. The definition of crystal really is that it's a system that has translational periodicity. But there is a way out. There's a solution. So here I've copied this picture from the previous slide. It's the same picture. And the trick here is to treat each atom not as a point, but as a wave. So we're going to think of each atom as a wave now. So here we go. I've assigned, for each atom, I've assigned a wave. And I've created a new artificial dimension. This is a one-dimensional crystal. But this new dimension is the phase of the wave. So for example, I can slide the wave up until it touches the atom. And I can do this for the next one. I slide a little further. Then I go even further, and so on throughout the crystal. And when I do this, I recover a new higher dimensional unit cell. I recover periodicity. So think about that for a second. We now have a repeating unit. This is the original, this is the real space projection of the crystal into the 3D space that we live in. And then you have an artificial dimension, which is simply the phase of the wave. You can slide it to move the phase. And this gives us a two-dimensional unit cell with new basis vectors. This basis vector does not point along the original direction of the crystal, but it includes a component in the new internal dimension. We call this the external space, and we call this the internal space. So the superspace basis vector has components in both spaces, and then this new direction points entirely in the internal space. So we recover periodicity in a higher dimensional superspace. This is the basic idea of superspace. In general, if you have multiple modulations, we get one extra phase dimension for every independent modulation wave. So if we have D independent modulation waves, maybe D equals 1, D equals 2, D equals 3, and so on, we achieve a 3 plus D-dimensional superspace. It's not so complicated. You know, it's an artificial new dimension, and we create it for our convenience. It's just a phase from 0 to 2 pi. So each atom in the unit cell has local properties, right? You're familiar with these properties. We have position, the atom position. You have a magnetic moment. You might have an occupancy. You might have a thermal ellipsoid. In a modulated structure, each atom still possesses these same properties, these local properties. But in an incommensurate structure, each atom also possesses an extended wave, having a k-vector, an amplitude, and a phase. And so an atom can possess a wave. For a modulation with wave vector k, we'll let A be the amplitude and phi be the phase. We'll let the atom be, this is the nth atom, so we'll place it at location r sub n in the first unit cell at the origin of the crystal space. And we'll let T be an arbitrary lattice translation. The modulation function then, as a function of position, has the usual form. It's just a wave. We can separate it like this, and we can see that it, as you change the lattice position, from one unit cell to the next, that the phase of the wave alternate, that it oscillates. And so the thing I want you to appreciate is that a wave belonging to one atom, this is the nth atom, also belongs to all of the translationally equivalent atoms. So all of these green atoms here, together they share one wave. And the red atoms, they have their own wave. Each atom in the unit cell has a wave that's connected to all of the other atoms of the same, that are translationally equivalent. So I will try to maybe illustrate this a little more clearly. These are really fairly simple ideas. When people hear about higher dimensional superspace, they get kind of queasy in the stomach, but it's really not so difficult to appreciate. Sorry, I think I can do this a little better. There we go. So if I take the red atoms, they share one wave. They have their own wave. I take the green atoms, they also share a wave. Now, there's several different symmetry inequivalent blue atoms. These have a wave, these have a wave, and finally, these ones have a wave. It's possible for them to cooperate. I can try and create a cooperative distortion here if I want to. Move everything in approximately the same direction. Right? Physically this makes sense, but in general these parameters are independent. And under certain circumstances they might not cooperate so nicely. They might do something else that's even more interesting. So all the translational equivalent atoms in the crystal share a wave parameter with amplitude and phase and K vector. Okay. Manuel Perez Mato gave a wonderful talk and explained that there are different ways to represent symmetry operations, the symmetry operations of a commensurate crystal structure. There's the sites notation, which I think is very intuitive. Computationally, or intuitively, the standard XYZ international notation is also quite useful. I like the point shift notation, where you take the point operation and represent it as a matrix. We often call this matrix R. And then you can also have a translational component. So you could like rotate and shift, or maybe reflect. Different types of symmetry operations. If you put the point and the shift together in the same matrix, a 4x4 matrix, this is especially convenient for computational work, because when you want to combine two operations together, you simply multiply these augmented matrices together to get the new point and the new shift. So it's a really nice way to go. This particular example is space group P212121. And so you see each one of these three operations is a screw axis, where you have a 180-degree rotation together with a translation that includes a component along the rotation axis. So these are not incommensurate symmetry groups. These are commensurate symmetry groups. It's also possible to represent the elements of a superspace group with matrices. But we have some issues. Space group elements like these ones, you can transform the atomic coordinates. You can transform the magnetic moments. You can transform the occupancies. If you have some polyhedra that are rotating, you can transform the rotation vectors. But ordinary space group elements don't have the ability to transform the waves that belong to an atom. Remember, in an incommensurate structure, atoms have waves. And you also need to transform the waves from one place to another when the atom moves from one place to another. So, for example, if I have a rotation of the crystal like this, and there's a wave attached to that atom, you can see that it doesn't look the same anymore. And so my symmetry operation, this is essentially not a symmetry operation, unless I also shift the phase of the wave. Similarly, with this symmetry operation here that relates two atoms to each other, I don't have a symmetry operation unless I also shift the wave. The idea here is that we need extra information in our new symmetry operators that transform the waves and shift them appropriately. And so we'll get a little bit mathy here. So here I have a superspace vector. It includes the ordinary XYZ components, loosely speaking. It has the 3D external space that we live in, where the crystal resides, has external space coordinates, and then you also have some extra phases. Remember, the artificial dimensions, the internal dimensions, they contain the phase shifts. So we have D of them, 1, 2, 3, 4, 5, up to D. In reality, D equals 1 is the most common. D equals 2 is also, quite interesting. There's a few rare cases with D equals 3, and to my knowledge, no one has ever seen encountered a structure that has 4 independent modulations. So up to, we'll say it's up to 3. And you stack these components in a single vector. External first, then internal, and then 1. So our new symmetry operators still have R. That's an ordinary external space point operation, like a rotation, a reflection, an inversion, rotoreflection, rotoinversion, something like this. And it still has an external space translation, V. But then you also have these new components down here. And the purpose of these new components is to treat the waves, to provide the correct phase shift for each wave. So when I take a superspace operation and multiply it by my superspace vector, it extends in this fashion. Each one of these pieces is a matrix. So R is just an ordinary 3 by 3 matrix. V is an ordinary translation, 3 by 1. Epsilon is a D by D matrix. So if I have 2 modulations, it'll be 2 by 2. Delta, this contains phase shifts. So this is a D-dimensional vector. And then the M part is a little strange. This is a D by 3 matrix. Sometimes it's 0, sometimes it's not. I'll talk about that a little bit. But this is how you apply a superspace operation to a superspace vector and transform both the atomic coordinates and also the phase shifts of the waves that belong to these atoms. So I copied this from the previous slide. This is the same thing that you just saw a moment ago. Here's the external space components. Here are the internal space components. So we'll do an example. This is we'll look at superspace group P4 sub 2 MC, which has two modulations, A0 1/2, where A is an irrational number, and also 0A 1/2. Here I show the in-plane components of the irrational components of the propagation vectors. They're also pointing out of the plane a little bit, right, because of the 1/2, but I don't attempt to illustrate that. We'll look at this diagonal C-glide. This is a C-glide operation, and this is the component. This is the XYZ, or the kind of traditional format for looking at this operation. Here's the external space part. That's Rx plus V in green. And then you have the internal space component, all of this stuff. In matrix form, it looks like this. Here's the R piece, the V piece, M, epsilon, and delta. Here's your external space coordinates. Here's your internal space coordinates. And when you apply this matrix to this vector, you get this form that's shown here. So, I mean, it's a little bit complicated, but at least it's straightforward. It's not mathematically difficult to implement. Here, for example, you can see that the X and Y components are reversed, and their signs are also reversed. They're switched and reversed. Here in the Z direction, you have a translation of 1/2. That's this piece right here. The two wave vectors get permuted, and so this takes the T and the U, and it switches them. So you have U on the left and T on the right. You have some phase shifts here. -1/4 to within an integer. Mod integers is the same as 1/4. So here I've got -1/4 and +1/4. You can see that this M part is non-zero. What that does is it causes the XYZ coordinates of the external space to get mixed into the internal space. So you see a Z here. That's because of these ones that come across and multiply by Z in the phase shift. So this is one example, one operation of one superspace group. You can also do magnetic superspace groups by simply adding time reversal to this operation, adding a prime, if you will. So this works perfectly well for either non-magnetic or magnetic cases. Now, I'm going to define a matrix called sigma. it contains the components of the wave vectors. So let's say I have two wave vectors, 1 and 2. Each row is a wave vector. And I simply, in lattice coordinates, I take the x, y, z components of the wave vectors and I put them in the matrix. Now, in general, this is an example. I can have both irrational and rational components inside my, my sigma matrix. So if I have alpha 0, 1/2, where alpha is irrational, I can split this up into two pieces. This is the irrational piece, and this is the rational piece. Now, the thing I want you to appreciate is that the M and the R and the epsilon components of the superspace group operation are not independent of one another. There's some relationships between them that are quite important. M is equal to sigma R minus epsilon sigma. Remember, sigma has the k vectors of the modulation inside it. I can break this up into an irrational piece and a rational piece. And since M has to be equal to this thing, and M can only contain integers, R, epsilon, and M all are completely integer matrices. Because this has irrational stuff in it, this piece has to be 0. And so I get one relationship here and another one here. So essentially, I can, through this relationship, if I know R, I can calculate epsilon. Epsilon is completely determined by R. And once I know epsilon, in the second relationship, I know the k vectors, I know R, I know epsilon, I can also calculate M. And so sigma and R are really the independent pieces. I define my k vectors, I define my point operation in external space, and then I can calculate epsilon and M and fill them in. The only thing that's undetermined here is delta, the phase shift of the wave. That's the only thing that's really free that I can adjust in this operation. So here's an example. This one here. So if these are my k vectors, and I have point operation that is the diagonal C glide here again. If alpha is defined numerically, then I can determine my epsilon matrix. So 0, -1, -1, 0 here. It's not free, it's determined. And then I can also calculate the M matrix once I have epsilon. And you can see the 0, 0, 1, 0, 0, 1. This is it's predetermined by the R matrix and the K vectors. Okay. Professor Peresmato spoke about the different ways to construct magnetic space groups from a non-magnetic space group. For superspace groups, it's pretty much the same game as for commensurate superspace groups. You have 4 construction types. You can start with a non-magnetic group F, we'll say a superspace group, and we can construct a variety of different magnetic superspace groups from it. So, for example, if you don't have any primed operations, if you're type 1 or colorless, the magnetic space group has exactly the same operations as the magnetic space group, superspace group, the MSSG, has the same operations as the SSG. If you have a gray group, the operations of the non-magnetic group are doubled. So you get all of the copies of the non-magnetic space group, and then that are not time reversed, and then you also get time reversed copies of each one. If you have a subgroup of index D, you can form either a type 3 magnetic superspace group or a type 4 magnetic superspace group. You simply select a subgroup of index 2, and you prime everything in the complement. Everything that's not in the subgroup gets primed, gets time reversed. If D has contains a subgroup of the point group of F, we call it type 3. And if in this case you have the same translational symmetries in both M and D, or M and F, and for type 4, you prime half of instead of priming half of the point group operations, you prime half of the translations. Type 4 is really the most complicated scenario, but also very interesting. So in summary, from one non-magnetic group, you can build a variety of magnetic groups. Here's one example. So this is P222 with one modulation along the, maybe gamma is something like 0.27 or, 0.15, something irrational. In any case, I can form a type 1 magnetic superspace group by simply keeping all of the operations and not priming any of them. I can form a gray group if I keep primed and unprimed copies of each operation. So that gives you the symbol 1' at the end. That's a new generator. I need to update this to the new symbols, the new uni symbols. I see that I haven't done that yet. You can form two different type 2 magnetic superspace groups. In this case, you prime half of the point group elements. And then type 4 operations are established by priming half of the translations, essentially defining some anti-translations. And I also want to join Manu in pointing out that when you prime a translation, when you time reverse a translation, it's no longer a translation, right? Anti-translation basically means not a translation anymore. It's when you shift the wave, and then I'll give you an example here. When you shift the wave, you can see that translation is not a symmetry of the wave anymore. Only if you switch it like that, then you have a translation. So again, you have to slide and then apply a point operation. Time reversal is a point operation. So this is the combination of translation and point operation. It's not a translation anymore. And we call it an anti-translation. So I think this is probably the most common case. Almost all of the type 4 magnetic superspace groups that you see in the Bilbao crystallographic server right now and Magen data are of this type. I found one exception that was, I think, this one right here, or of that type. So anyway, this is the anti-translation for each of these examples. So there are a lot of these groups. If you look only at the non-magnetic superspace groups, we found quite a few of them. In 2011, we, I think, published the first comprehensive list up to D = 3. And there's close to 14,000 non-magnetic superspace groups that can be found. And so these have all been tabulated. And most recently, I think 2 years ago, we published an enumeration of the magnetic 3+D dimensional superspace groups. And the number is truly astonishing. So here we have 230 normal commensurate space groups, 32 crystallographic point groups. You're familiar with those. If you look only at D = 1, you've got 775, up to 12,000 of the type 1. So these are magnetic superspace groups, but they're completely analogous to the non-magnetic ones. And then when you go to type 2, the number just gets so much bigger. Type 4, you've got 176,000 type 4 magnetic superspace groups with 3 dimensions. And so all total, if you add them together, there's almost 350,000 of these symmetry groups. With so many groups, you might wonder, why even bother? Why go to the trouble of identifying the groups? Well, when you have two different presentations, maybe you have two research groups here that have worked on the same material. They both analyze the symmetry. They both present a crystal structure. And it's actually really difficult if they're presented in different settings of the superspace group to be sure it's the same structure. It's really hard. It's a non-trivial problem. And so, one advantage of correctly identifying the each superspace group and having a transformation to a standard setting is that it's possible to test equivalence. If you try this sometime, you'll see what I mean. It's challenging to know if the two presentations of the same structure are really the same structure or not. You need some computational tools for this work, and those tools depend on having such a table. let's talk about the symbols for just a moment. So a magnetic superspace group symbol has several different components, and it's really quite easy to understand. First of all, in the limit that you take the modulation amplitudes and turn them to 0, you just kind of continuously turn off the modulations until they disappear. This is the resulting commensurate magnetic space group. We call it the basic magnetic space group. If it's a non-magnetic case, we just call it the basic space group, but it's commensurate. In this case, it's P4 sub 2 prime, MC prime. So 2 of the generators are primed. These are space group generators. I didn't really prepare any slides on space group generators, but the idea is that if you take these elements and you include them in the group, that you can multiply these elements together in arbitrary ways to get all of the other elements. So it's a sufficient set to generate the whole group. And these generators, they have meaning. A 4, for example, means you have a 90-degree rotation perpendicular to the primary, running down the primary axis. The M in the second position, this means you have mirror planes that run through the crystallographic axes. And then the third symbol, that corresponds to the diagonal directions. So for this particular example, this indicates that along the diagonal direction you have a C glide. So you apply a mirror plane and then you slide down into the screen. So in any case, these things here with the alphas, I think that's supposed to be an alpha, not an A. I apologize. These are the propagation vectors. So alpha 0, 1 half, alpha 0, 1 half, 0, alpha 1 half. Those are the propagation vectors, and these are the phase shifts of the waves. So for each generator, 1, 2, and 3, you have a phase shift. You see 1, 2, 3. These are the phase shifts of this wave. These are the phase shifts of this wave. So for example, if I apply the mirror plane, that's the second generator. So this wave will transform to a new location and then shift by 0. So there's no phase shift for that one. But if I apply the C glide, this wave will transform to the atom will transform to the new location and then experience a phase shift Q, which means 1/4 of a period. 1/4 times 2 pi. So that's going to be pi over 2, a 90-degree phase shift. There we go. Sorry. With this second wave, when you apply the 4-fold rotation, there's no phase shift. When you apply the mirror plane, you get a phase shift of 1/2, which is 180 degrees. And when you apply the C glide to this wave, you get the ordinary transformation plus a 90-degree phase shift. I hope that helps a little. These 00Q, 0SQ, these are the components of delta. These are the phase shift components of the. Remember, from R and V, I can immediately determine M and epsilon, but this is free. I have to determine it separately. I have to specify it. It's placed here in the symbol. All right. So let's talk about the magnetic superspace group number. In superspace, you have an extent. Remember, you added artificial dimensions to recover periodicity. There's a lattice in superspace. And we talk about the Brave class of the lattice. So 2.65 just means it's the 65th lattice in 2 dimensions. That's all it means. And this is the Brave symbol, Brave class symbol. There's no phase shifts for a Brave lattice. This is called the family superspace group. This means that if you take all the primes away, remove all the time reversals, but keep all the elements, this is the non-magnetic superspace group F, from which we construct the magnetic superspace group. You can see that this has space group P4 sub 2 MC in it. This is the basic space group 105. This is the Brave lattice, and this is the 9th superspace group that can be constructed from this space group, from this family space group and this Brave class. The magnetic basic space group, this is just 105.214. This is a BNS number. for the magnetic basic space group. This means that it's constructed from non-magnetic space group 105, and it's the 214th magnetic space group in the tetragonal family. That's what the number means. And finally, the MSSG number combines all of this information. You can see the Brave class, you can see the basic space group, you can see the magnetic basic space group, 105, 214. Both pieces are there. And then finally, the 1 just means that if you combine all of these classes together and start constructing multiple magnetic superspace groups, this is the first one in the list. That's the meaning of the symbol. I hope that's helpful. So, a couple of examples. Let me see how I'm doing on time here. I think it's probably just about out of time for this topic. So, dysprosium manganese germanium 6. You've seen this one presented. It's a double conical structure. It's actually really beautiful. It's got, for each of these helical waves, you've also got a ferromagnetic component, which transforms the helix into a cone. I think I've got a picture of this. You can take a look. I extracted this from the Bilbao Crystallographic server, from the Magen database, and did a screen recording. So you can see both conical periods. Now we'll add some unit cells along the z-axis. I don't know why it shrinks like this, but you can expand it again. And then you can turn on the evolution of the wave phase. Slow it down a little bit so you can see it, and you see there's 2 spirals. So the dysprosium and the manganese each have their own spirals, and they point in roughly opposite directions. But they spin in the same direction. So you can see that again. If you look carefully at the green and the purple arrows, they're directed in almost opposite directions. So it's really quite a spectacular structure. I think it's beautiful. These are the symmetry elements of the group, the superspace, the magnetic superspace group. -1 means time reversal at the end. And it's a single case structure. So both spirals, have the same K vector. So remember that symmetry operations always constrain the degrees of freedom. They reduce the number of parameters in your structure. The external parts, R and V for each of these operators, for each of the symmetry operators shown here, the external part constrain the positions and the magnetic moments of the atoms. So here you can see the magnetic moments so this is the position and the magnetic moment, position, magnetic moment, and so on, position, magnetic moment. And germanium doesn't have magnetic moments. This is the form. You can see that you have this parameter, the x component of the moment, fixed at 0. This one's fixed at 0, and this one's free. This is called the sim form. It shows the what parameters are free. It's quite restricted by the symmetry operations. These are the modulation vectors. So these are the cosine and sine. It gives you a real and an imaginary part of the component of your vector. So for the dysprosium atom and K vector number 1, magnetic moment component along X has both a real and an imaginary part. And you can see in this case, the imaginary part is fixed at 0, but the real part is free. For the Y component, both of these pieces are fixed according to this parameter, so they're not free. Once you define this value, you also define these. And so that's actually fixed. And then the Z component is constrained by the superspace, magnetic superspace group to be 0. And then for manganese, it has its own set of parameters. It's actually got 4 independent parameters there. If you look at these numbers and study them, I'll copy them to the next page. You find that the X component and the Y component of the dysprosium moment are the same, so it's a circular wave. since the X and Y components are equal. And you can also determine the phase, of the relative phases of these components. It looks like they're about 60 degrees apart. For manganese, you also find a circular spiral, and the phase here is almost 180 degrees different from dysprosium to manganese, and that's why those two vectors point almost in opposite directions, but not quite. Here's another example. This is multiferroic terbium manganite. So these are the superspace, magnetic superspace group operations. And in this case, if you look closely, you have external space, internal space, really quite simple. You just have only a phase shift and a time reversal. So remember, this is one of those anti-translations I told you about, where you shift and then time reverse. So I think it's quite an important symmetry operation in this structure. Anyway, if you look at the constraints of these symmetry operations on the magnetic modulations, you'll see that there's only 1 degree of, or actually 2 degrees of freedom, and for physical reasons they end up being approximately the same. Oh, I lied. I apologize. I just said something wrong. In this case, sorry. In this case, it turns out that the symmetry group does not constrain the magnetic modulations. In this case, the constraints come from somewhere else. They come from the irreducible representations that are active in the structure, and we'll talk more about that later. So these are actually not symmetry constraints. They're constraints of the representations relevant to the structure. More on that later. This is a picture of the modulation. It's actually beautiful. You've got simultaneous transverse and longitudinal magnetic waves, 90 degrees out of phase, that give you a cycloid. So animating it just helps to visualize. In actual reality, it doesn't have to be active and dynamic, but evolving the phase helps you to see and understand the structure more clearly. So it's quite significant that the longitudinal and transverse modulations by themselves do not break inversion symmetry. But together, these two waves combined provide a hybrid mechanism for breaking inversion symmetry and coupling to a secondary ferroelectric moment. So that this material actually was very controversial in the literature 15 years ago. A lot of papers debating about whether it was, ferroelectric or not. And at that time, the infrastructure for understanding the problem was not so good. But now we have really good infrastructure, and it's very easy to see why these two modulations together break inversion symmetry. The magnetic skyrmion lattice is another interesting example. In this case, you actually have 3 modulation vectors, 120 degrees apart in the same plane, with a fixed phase relationship, so they're phase locked to each other. And because all 3 vectors are in the plane, 2 of the k vectors are actually, or the last k vector is actually related to the other 2. So you can see that k3 equals minus k1 minus k2. And when one k vector can be written in terms of the other k vectors, it's not independent. And so it doesn't get its own superspace dimension. Only the independent k vectors get superspace dimensions. And so this is actually a 3 plus 2-dimensional magnetic modulation. Anyway, it's a very interesting system. And if you look at the magnetic superspace group operations of the magnetic superspace group, you can see that they constrain the moments so that the structure has only 1 degree of freedom in the plane. It's quite interesting. It's a very complicated structure, but it only has 1 degree of freedom in the plane. There's another degree of freedom out of plane with a real skyrmion. You can see these vectors have an out of plane component as well. So there's actually 2 degrees of freedom in total. If you look at the Magen data database, there's all sorts of interesting examples. This is a rather spectacular 3 plus 2-dimensional case. I don't know why, but the server was kind of running a little slow when I tried to make the movie, Manu. So it's a little jumpy, but you can see It's a very interesting phase evolution there. And then the manganese germanium structure actually has some ambiguity. Vladimir Pomyakushin and colleagues published this structure, and they actually gave several structures that all fit the data equally well. And so I think we're just presenting one of them here. But that one, there we go. It's a little jumpy. You can see some rather spectacular 3D evolution. It's a fully three-dimensional. So it's a three-modulation structure, cubic structure. Fascinating spin texture. Maybe Dimitri, I don't know if you'll talk about this one, but it's a nice example. Okay, so in summary, incommensurate modulations destroy 3D translational periodicity. And we create superspace dimensions to recover the periodicity. You get one superspace dimension for every independent k-vector, where the irrational part has to be independent specifically. Every active k-vector, every modulation has to be an integer linear combination of the independent ones. Modulations can be magnetic, displacive, occupational, rotational. They can even be thermal ellipsoidal. Many different types of modulations, not just magnetic ones. Superspace symmetry operations transform both the local properties of the atom and also the waves attached to an atom. Magnetic superspace groups are constructed from superspace groups by adding time reversal, just like was the case in Manu's talk on commensurate magnetic space groups. There are many, many, many magnetic superspace groups, hundreds of thousands of them in total. Probably most of them will never be realized in real structures. But it's important to know what your magnetic superspace group is so that you can compare it to other structures and be sure it's either the same or not the same. It's also important to the physics of the material. You need to know the symmetry group in order to understand what tensor properties are possible and to constrain the degrees of freedom so you don't have so many parameters to refine in an experiment. So anyway, there are a variety of tools available in the ISOTROPY software suite for treating magnetic superspace groups and incommensurate magnetic structures. I've already shown you the table. We'll be working more on this tomorrow. We'll spend several hours, I think, looking at some examples, so we have plenty of time. I'll just point out that the FineSim and ISOSIF tools in the ISOTROPY software suite are really quite powerful. You can import a magnetic structure and automatically detect the magnetic superspace group, and then enforce it and export it in the correct symmetry group, transformed into whatever setting you like. So this is a nice tool. This commission, the same speakers that you see here, met together in Erice in Italy in 2019. And I think over lunch, Manu and I had a conversation about detecting superspace group symmetry. And a few months later, Harold and I, we got this working. So I think it works fine. IsoDistort has the ability to create incommensurate magnetic structures. So if you want to build models, you can very easily, with a user-friendly interface, construct incommensurate magnetic structures with the correct symmetry group and export them for refinement. Let's see. I think there was maybe something else. Yeah, sorry about that. I jumped too quickly. No, I guess that was the end. So we will look more at those tools later. Should we take a 5-minute break, and then I'll give a very brief introduction to the ISOTROPY, actually to just representational analysis in general. So thank you. But different topic. So I'm also today and tomorrow introducing the tools of the ISOTROPY software suite, but I thought it would be a good idea maybe to start with just a little bit of information about representational analysis. I've talked to many of you and have discovered that many of you want to learn more about representation theory, what it is. So I'd like to acknowledge my primary collaborator, Harold Stokes. He, again, he and Dorian Hatch initiated the ISOTROPY software suite many years before I joined the team. But I've been a member of the team for almost 20 years, not quite, maybe 19. And then also, others have made significant contributions to the tools and the features the infrastructure that we use in the ISOTROPY software suite. I'd like to recognize the IUCr Commission on Magnetic Structures, who are providing most of the lecturers for this event, and specifically Manuel Perez Mato, who you heard from yesterday, and also Moise Arroyo of the Bilbao team. Alan Coelho, the developer of Topaz, have interacted with me and adopted some features that allow refinements to be easily exported to Topaz. Vaclav Petracek of the Yana Group has taught me much of what I know about incommensurate structures. I'm grateful for that. Juan Rodriguez Carvajal and also Brian Toby and Bob Mondriel have also given me a lot of good ideas and helped to create interfaces that allow FullProf and GSAS to be used in conjunction with the ISOTROPY software suite. I'm grateful to they've given me some of the best feedback. I really appreciate bug reports. Please send more. So the purpose of the ISOTROPY software suite is to support the use of representational analysis to parameterize the symmetry breaking distortions of a crystal. Now these distortions might arise in a phase transition, or it might simply arise from a comparison of two different structures, one of which has a lower symmetry than the other. So you don't have to have a physical phase transition to use this tool. You can compare two structures to see how one is distorted relative to the other. So the undistorted structure is called the parent structure. I think most of you are familiar with that term. While the distorted structure is often referred to as the child. The space group of the child is a subgroup of the space group of the parent. That's the basic. If you're doing representational analysis of any kind, this is the situation that you have. The individual distortion parameters have different names. I call them symmetry modes in my work, but I think if you talk to Juan, he'll often call these basis functions. I think that is even maybe an older and more correct term. In any case, the traditional parameters are the individual parameters of an atom. You might take an atom and look at its X, Y, Z components of its position, the X, Y, Z components of its magnetic moment, and you can describe a magnetic structure by specifying the coordinates and the magnetic moments of each of the individual atoms. When we do symmetry modes, we're specifically using parameters that belong to an irreducible representation of the parent space group, or the parent symmetry group. So these are global patterns where one parameter moves many atoms in the crystal, an infinite number of atoms. And so it's a different parameter set than the traditional parameter set. And I'll try and explain the relationship between the two. So here are some high symmetry parent structures, each of which is cubic in this case. And then here's some distortions. This is a displacive distortion. This is an occupational distortion. This is a magnetic distortion, right? It's when I say distortion, I mean a symmetry breaking influence. Adding magnetic moments typically breaks some of the symmetries of the parent. In general, any physical or mathematical system has symmetries. You can just visually see, you can look at transformations of a molecule. You can see icosahedral symmetry of this macromolecule. You've got a continuous Lie group symmetry on this object. Crystals have space group symmetries or superspace group symmetries. And then the universe itself, the fabric of space-time, has symmetries. We still don't know the symmetry group of the quantum vacuum. This is still something we're very actively, not me personally, but which the scientific community or the human race are trying to understand. Anytime you have any kind of symmetry group that can be broken, any kind of symmetry that can be broken, you can use group representation theory to parameterize the symmetry breaking influences. So most of you know what a group is. I discovered that a few don't. Please don't be offended by my going to such a basic level. I just thought it might help some people. A group in general is a set. It's a collection of objects or elements that can be combined with a binary operation like addition or multiplication. So if you If you want to group, you need to make sure that your binary operation obeys these rules. So closure means that if you multiply two elements of the group together, you get another element of the group. The identity just means there's an operation that does nothing, or an object that does nothing, like adding 0 or multiplying by 1. Every element in the group has to have an inverse, like adding 3 and minus 3 to get 0, or multiplying 3 by 1/3 to get 1. And then associativity is well understood, I think, by everyone. So the symmetries of any physical or mathematical system form a group. So if we can, for example, take this object here, which has the identity operation and also 3 180-degree rotations, 3 two-fold rotations about these 3 axes. And if we apply the x rotation and subsequently apply the y rotation, the result is equivalent to only applying the z rotation. So basically, x times y is z in this case for this group. So this is a multiplication table. It shows you if you take any two elements and multiply them together, it shows you the resulting object. Now, a group representation is a little bit different than a group. Right? This is a group representation is a mapping of symmetry elements to, I'm not sure what I did there, I apologize. It's a mapping of symmetry elements to matrices. So here you've got 2x being mapped to this matrix, 2y to this matrix, and 2z to this matrix. And if you look carefully, you'll see that the x matrix multiplied by the y matrix gives you the z matrix. So these matrices obey the same multiplication table as the group, and therefore they are a group representation. In general, the matrices can be complex, but in this case, I'm showing you a real representation. So this is also a representation of the same group. In this notation, the -1 up here, or the bar on top, means minus. So you have -1, +1, and -1. So you see x times y equals z. It's a valid representation of that group. Here's another valid representation. X times y equals z. And finally, here's a two-dimensional representation. This is the one from the previous page. And you can see that, again, x times y equals z. In this case, the bottom representation is actually the direct sum of the upper representations. So I put R1 in the upper left-hand corner, R2 in the lower right-hand corner, and I essentially constructed a two-dimensional representation from two smaller representations. So this is, we say that R3 is reducible. It can be reduced to R1 and R2 as a direct sum. An irreducible representation can't be separated into smaller matrices. The irreducible representations are the really interesting ones. I like to call them recipes for symmetry breaking. We use the word irrep a lot. Irrep just means irreducible representation. And I will show you that they are recipes for symmetry breaking. So here is a representation of some group. I'm not going to tell you what group it is. It's just some group with 8 elements. And this is the group representation. And it's an irreducible representation in this case. So how do I break symmetry? Well, I start with 8 symmetry elements. And I pick an abstract, or just a direction in the abstract space where these matrices live, two-dimensional space. And I check to see which symmetry elements leave the order parameter. We call this the order parameter invariant. In this case, I think if you look closely, the identity leaves it invariant. And this matrix also leaves it invariant, because when you do -1, -0 is still 0. And so, but all of the others, like this one here, for example, this is going to be -A0, which is not the same. And if you apply this matrix here, you're going to get 0A, which is not the same. So only G1 and G2 leave it invariant. It's called the order parameter direction. There's also other directions. If I choose this direction here, AA, G1 and G5 leave that vector invariant. And finally, if I choose the lowest or the most complicated direction, Only the identity leaves it invariant. And so here I have 3 different symmetry groups. This is a subgroup of the original group. I threw most of the operations away, and so I broke the symmetry. I'm actually, in this case, using space group P4 over mm, or P4mm. And these are the operations that are of interest. There are also translations, but no new matrices. The translations end up having the same matrices that you see here. So, in any case, the symmetry breaking that I did when I found the subgroup that leaves this order parameter invariant, that gives me subgroup PM, which includes the identity and the y-axis mirror plane only. So from one IRAP, I can break the symmetry in multiple ways. And the subgroups are called isotropy subgroups. Okay, these are isotropy subgroups. Okay, let's look at that example A0 again. So I copied all of this information from the previous slide. It's the same stuff. And you can imagine that I have a unit cell for this space group, P4mm. When I break the symmetry with the A0 order parameter and preserve only the y-axis mirror plane, you can actually see that preservation. So in this case, that IRAP causes a strain. It causes a shear of the unit cell. The top of the unit cell and the bottom of the unit cell move in different directions. You can see that shear here. That destroys this mirror plane. It destroys this mirror plane. It also destroys this mirror plane. But this mirror plane survives the distortion. And so A0 is an abstract order parameter direction. The strain is a physical order parameter, but there's a correspondence between them. A symmetry element that leaves the abstract order parameter direction invariant corresponds to a representation matrix that leaves the abstract order parameter invariant corresponds to a physical symmetry operation that leaves the child structure invariant. So that's one of the big ideas of representation theory in this context. Juan is going to talk about magnetic representation, so I'm not going to talk about that slide. Okay, this is an object that at least has point group 222. It has 180 degree rotations around each axis. And if I color one side black and the other side white, I can think of that as a distortion. We'll call it a color distortion. It breaks the symmetry. It eliminates the z-axis rotation and the y-axis rotation. So it breaks some symmetry. And if I apply a twofold rotation around the x-axis, you can see it reverses the direction. If I apply a twofold rotation around the y-axis, the structure is preserved. And if I apply a twofold rotation around the z-axis, the distortion is reversed again. So here are the 4 irreducible representations of point group 222. I would ask you the question, which one of these irreducible representations is like this p orbital? It should be obvious that it's this one down at the bottom, because the x and the z reverse, so you have -1, whereas the identity and the y rotation don't. And so this physical distortion has a relationship to one of the irreducible representations. We say that this function, this shape, this distortion belongs to IRAP gamma 4. That's the word we use. We say it belongs to it. I want to talk about what it means to belong to an IRAP. If we had oriented the orbital in a different direction, it would have corresponded to one of these other IRAPs. You can also do this with d orbitals. So I don't want to, belabor the details, but this shape is like IRAP gamma 3, and you could look at all the d orbitals and associate each one. Each one of them belongs to one of the irreducible representations. But this shape does not belong to any of the irreducible representations. When you belong to an IRAP, we call it an IRAP basis function. Mickey Mouse is not an IRAP basis function. It doesn't transform nicely like this. Only very special shapes, very special functions very special distortions, belong to IREPs. Okay? In general, most shapes do not. And it's really important in your system to find out which basis functions correspond to the irreducible representations. So in general, IREPs, I like to say, take symmetry theory from being merely a beautiful or aesthetic construct and turn it into something that's hardcore computable. You know, you can do calculations on symmetry, on the symmetry of a system, if you know the irreducible representations of your symmetry group. So here's a very general example. This is I've just taken a lattice with space group P4MM, and I've broken the symmetry by extending the size of the unit cell in both directions, and also reducing the point symmetry to P1, or to 1. So now, in 2 dimensions, I have 8 degrees of freedom. And I can take these 8 degrees of freedom and I can stack them in a vector, and I can call this my 8-dimensional distortion space. By assigning values to each of these parameters, I can achieve any possible distortion in that unit cell. These are the traditional parameters. Each individual atom has a magnetic moment or a displacement. These are the symmetry mode parameters. I also have 8 of these parameters. So there's 8 traditional parameters and 8 symmetry mode parameters, because each of those arrows is 2-dimensional. So it actually contains 2 parameters each. So there's 2 plus 2 plus 2 plus 2 is 8. But these patterns transform using the coefficients from IREP matrices, gamma 5, M5, X3, and X4. Don't worry about those names right now. So by adding these together and mixing them, I can achieve any distortion that I can achieve traditionally. So they provide an orthogonal and complete basis for the space of all possible distortions. In general, that's what IREPs are good for, a complete and orthogonal basis of distortion space, and a very convenient and a very natural basis. Okay, so we've talked about modulation wave vectors. Basically, symmetry modes, IREP basis functions in crystals are waves. So they all have a k-vector. You have to go to some position in reciprocal space, and if you see some superlattice intensity in your diffraction pattern, you know you have a modulation with wave vector 1/4, 1/4, 0. And so you ask, what IREPs live at that point? Two different points in reciprocal space have different IREPs. Every point in reciprocal space has its own IREPs. Sorry. So anyway, IREPs are defined for specific k-vectors. These k-vectors have names, traditional names that were established by Cracknell, Davies, Miller, and Love many years ago. I don't memorize these names. If you can memorize them, that's fine. I look them up in tables. For every Bravais lattice, they're different. But, you have A, R. You see IREP labels like Z5+, and you wonder, what is Z? It's some tabulated name. Okay, they're somewhat arbitrary names. The star of a k-vector is the set of all symmetry-related k-vectors relative to the reciprocal space group. So, for example, if I take the vector 1/2, 0 for a tetragonal group like P4MM, minus 1/2, 1/2, minus 1/2, minus 1/2, these points are all related by symmetry. So they belong to the same k-star. 1/2, 0 also has a star. 1/4, 3/4, 0 that has 8 k-vectors in the star. They're all symmetry related to each other. When we look at a space group, a complete space group IREP, it's actually an IREP that corresponds to all of the arms of the k-star simultaneously. You may hear about little group IREPs too, that correspond only to a single k-vector. But typically we want to find representation matrices that cover or take care of all of the k-vectors at once. But we don't have to list all of the arms of the star of k. Typically, we choose a representative k-vector or set of k-vectors that are not related by translational symmetry. If you look at this vector here and this vector, The difference between them is 1, 1, 0. That's a lattice vector. And so we don't need to include this one. We only mention this one. Why do we do that? Well, it turns out that if you have 2 points in reciprocal space that are related by a lattice vector, they have the same IREPs, so you don't have to think about them. You only need to take the ones that are not related by translational symmetry. And if you have an incommensurate wave vector, then, probably all of them are not going to be related by lattice vectors. So, in the interest of time, there's not a ton of time. I'll just say that it took many years to tabulate and to discover the irreducible representations of space groups. The little K-group IREPs were found quite early, back in the 1960s and 70s. Between 68 and 84, the complete space group IREPs that cover all of the arms of the star of K were, a couple of cases were done manually, but it's quite hard work. My collaborators, Stokes and Hatch, in 1984 and 1987, I think made quite a monumental advance. They tabulated all of the space group IREPs at special K points. So these are points at the vertices of the Brilliant zone, at the corners, not in the middle, but in the corners of the Brilliant zone for special K points. Later, in 1982, Moise Arroyo of the Bilbao team, and also Stokes and Hatch at BYU, developed real-time calculations that could calculate complete space group IREPs at any commensurate K point. And those are very powerful tools that are still in use today. In 2014, Harold and I found a clever way using superspace to tabulate all of the space group IREPs for any K point so that no real-time calculations are required anymore. There are tables from which you can easily construct the IREP for any commensurate or incommensurate K point. And these are available within the ISOTROPY software suite. And anyone else that wants to use them in their software is welcome to download them and can do their own projections of IREP basis functions. So, isotropy subgroups. You start with a parent, you break symmetry, you wind up with a child. And the child is called an isotropy subgroup. It's the low symmetry subgroup. If you have a parent and you want to specify a particular isotropy subgroup, you need to pick the K vectors. It might be 1 point or it might be a superposition of K vectors. For each K vector, you need to choose an IREP. And then once you've chosen your IREPs, you have to choose an order parameter direction. Remember A0, AA, AB, those abstract vectors in the carrier space of the IREP. And once you do that, you arrive at an isotropy subgroup. But there are multiple paths to reach the same point. You can sometimes have multiple IREPs that take you to the same isotropy subgroup. An isotropy subgroup is completely specified by a space group type, or maybe a superspace group type, a basis, and an origin. So what do I mean by this? Let's see. If I navigate here, please give me just a moment. We'll go to the workshop, ISO tutorials, visualizations. I think you also have these files. You can look at them later. So here, for example, this is tungsten oxide at room temperature. So if I turn the distortion to 0, this is the high symmetry parent, and this is the child. The unit cell of the parent is the small box. The unit cell of the child is the big box. And so you can see that it has a different basis. It has a different space group. It's not cubic anymore, it's monoclinic. So we have a different space group type, we have a different unit cell or a different basis. And also you see that the origin of the parent unit cell and the origin of the child cell are at different locations. So you have 3 pieces of information: space group type, basis, and origin. Remember those 3. Here are some distortions of this high symmetry parent that all have the space group P2. So P2, 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 P2. Parent and child, both P2. But the basis is different. And so these are definitely different isotropy subgroups. Different distortions. So basis matters. Here are two children that also have space group P2, and the parent and the child have the same basis also. Same space group, same basis. Different distortions. In this case, the origin is different. So origin shift also matters. So to specify an isotropy subgroup, you need all three pieces of information. I think it's important to remember that. I think I am out of time. Time is over, right? Yeah. So I have, I think, a couple of hours to spend with you tomorrow. I'll walk through some of the tools of the isotropy software suite during the first hour, and then we'll have a couple of hours for you to do hands-on tutorials, and we'll see you then. Thank you.
Thank you, Branton. So now the lecture open to question and the comments.
I have a question of the previous lecture. What's the physical meaning of M and epsilon?
Yeah, I have hearing aids. I don't hear very well. I apologize.
I mean, what's the physical meaning of M and epsilon in the transformation matrix?
The meaning of epsilon?
Yeah, M and epsilon.
Yeah, the epsilon part of the operator permutes the k vectors.
How do
So, for example, if I have, let's say I have three k vectors,
Yeah.
pointing along the x and y and z directions. In that case, epsilon is a 3 by 3 matrix, and it literally, if you have one, let's see. Let me go back and look at that example. That's a really good question. I like your question. Let me just go back to the slide right here. So we go down to this example here. Sorry. Where did it go? Hitting the wrong key. There we go. So in this case, K1 gets mapped to minus K2, and K2 gets mapped to minus K1. So it transforms, it takes the K vectors and permutes them, and can also reverse them.
So you mean it's the symmetry for the k vector?
Yeah,
Okay.
yeah. In the internal space, the phases of the K vectors are the internal space dimensions. And so it also tells you that the phase of K1 will become minus the phase of K2 after transformation. So if the waves change places, because it's a diagonal mirror plane, right? Then epsilon is telling you how the phases of K1 and minus K2 are going to be related to each other.
Okay, then what's the meaning of M here?
The meaning of
Yeah.
I hoped no one would ask me this. Of course you have to ask it. It's like, I was avoiding this. If M is not 0, it's evidence that you haven't chosen a very nice unit cell. If you choose a nice unit cell, if you change, you can always change the setting of your group, right? Manu talked about setting transformations. They're so important. They're really boring. They're tedious. They're annoying. But only when you master setting transformations do you feel comfortable, I think, manipulating your structure and its presentation. So if you choose a better times, and there's always a nice setting. It's called a super-centered setting, where you add some centering vectors. And when you do that, M beautifully goes to 0.
Okay.
So it's an annoyance. That's what it is. So what is it? Annoyance.
Okay.
If if you have rational components in your k-vector, like what you see right here, let's see, there we go, yeah. If you have rational components like half-half, that will cause M to be non-zero. And that will be evidence that you haven't chosen a good setting.
Okay.
Yeah.
So that's not related to any symmetry.
Yeah.
Okay.
Yeah. Ideally, you don't want to have rational components in your k-vector. Yeah.
Okay.
But,
Thank you.
But honestly, for convenience, if we keep the setting the same as the parent, then, you know, that's also nice for other reasons. But it creates this complication.
Okay. Thank you.
Mm.
Okay, is it okay to make tea break? Okay, let's thank Branton again. Thank you very much. So we will start on 10:20.